Assalamu alaikum warahmatullah. Welcome to this lecture number 8 for our subject mechanical vibrations. And if you recall the topic we discussed before the midterm examination, it was about the transfer functions, Laplace transform, which was a technique to convert the differential equation of the mechanical vibration system into an algebraic equation, which makes it easy to solve. And then there's a specific thing in the Laplace transformation is a transfer function, which is a Laplace transform output over the input of a system. So we mostly we do it considering the zero initial conditions, and then we can later on add the initial conditions in our Laplace transform function. uh, but there is a thing about the Laplace transformation that uh, if you consider the transfer function that we discussed last time, so more specifically we can call it a general transfer function, where if the force being applied is f of t, we can transform that into f of s. And if you recall that I told s is a Laplace variable, complex Laplace variable. It is equals to gamma plus iota omega. So this part tells us about the transient response of a system, and this tells us about the steady state part. Steady state response. So whenever any system is excited, so it has a two different regions of its response. The first one is the transient response, the time it takes to settle down to become stable. That is considered as a transient response. And then we have the steady state response. So maybe from 0 to any time t, we have the transient response, and from that time t up to the infinity, we have the steady state response of a system. So let's say if you applied any load onto a mechanical vibrating system, so probably it vibrates like this in the beginning, and the vibration was increasing, and at certain point now it's kept on vibrating with the same amplitude. So this is your transient region, and then you have a steady state region. We have discussed all of these things earlier. So we can evaluate the response of a system, the solution of a system. We can solve a mechanical vibrating system using that general solution technique we have seen in the beginning for the second order differential equation. We can do that using the Laplace transformation. We have also seen that one in the last lecture. And that Laplace transformation, or the transfer function of that, uh, gives us the holistic view of both the transient response and the steady state response of a system. But in most of the cases, specifically in the mechanical systems, uh, majority of the loading in our cases are sinusoidal in nature, and we are more interested in what will be the long-term response or the behavior of a system. Let's say, consider an example of a washing machine. If you have seen a front load washing machine, it's like this one, and you put clothes inside, and that washing machine rotates at a very high rpm, and because of this rotation there's some force, that's like a centrifugal force, and that force, because it is acting at tangentially at every instant, so that causes vibration in our whole structure. So obviously we are not interested in what will be the response of the machine mechanically when I switch on the machine. What will be the response in the first 5 seconds? I'm interested in what will be the response of a machine, because I'm going to run the machine for 1 hour, 2 hour, based on how much laundry you have. So I'm more interested in the steady state response of a system. Another example, you have a bridge over this, we can say, seashore, or over a river. So that bridge obviously will be receiving some with certain velocity. So we are not interested in what will be the response of the bridge in first 5 seconds or first 10 seconds until it stabilizes. We are more concerned with what will be the long term behavior of this bridge. So that's again the steady state part. Although we are also concerned with the initial response of a system for the safety concern, like for the threshold, like it can receive maximum gust of 50 kilometer per hour. Let's assume not beyond that. But what if it continues to receive a wind gust of 40 kilometer per hour for 1 hour, for 60 minutes? So that is also a concern, because most likely some of the component of the bridge or any other structure will undergo fatigue, and it will cause damage to certain structure, and we don't like it. So that's why, just sum it up, we are more interested in the steady state response in certain cases. So for that, we have a special kind of transfer function that's called the sinusoidal transfer function. Uh, so that is termed as the sinusoidal transfer function, and obviously when sinusoidal input is applied to the linear time invariant system, as we have discussed earlier, that Laplace transformation is applicable only to the linear time invariant system, even if the system is non-linear. Even if the system is non-linear, you have to convert that system into a linear system mathematically and then apply the Laplace transformation. So we can, when a such system is subjected to a sinusoidal force, the system will tend to vibrate at its natural frequency. And not only its natural frequency, it will also vibrate at the frequency of the input force. So let's say you have take an example of mass spring damper system. So whenever a sinusoidal force is applied equal to F naught sine omega t. So once it is applied, system has its own natural frequency. So because of the application of such load, it will start to vibrate not only at its natural frequency, rather it will also vibrate at a frequency of the applied load with some lagging, which we call phase angle, which we quantify using a phase angle actually. So, if the damping is present, the portion of motion not sustained by the sinusoidal input will gradually die out. So, and as a result, the response at steady state is sinusoidal at the same frequency as the input. So, with the presence of damping, the portion of the system which is outside the frequency of the applied load, it will damp out, it will wipe out, it will vanish, and the response of a system at for the steady state would be of the same frequency of the applied load. So that's why we are more concerned with the applied frequency as well. So sum it up. We just sum it up. So as we know, the Laplace variable is gamma plus iota omega. So we are not concerned with this part. Now we'll just substitute Laplace variable equals to iota omega, or maybe in some books you will find j omega, but both are complex number where I is equal to j is equals to under root minus 1. So both are complex number. So a lot of theory of the complex numbers will be used in this section, in this chapter. So I hope you are aware with about those. So that it is also called as, so this whole method of studying the steady state response of a system due to the sinusoidal force, uh, based on a frequency, actually that's whole method is called the studying the frequency response of a system. We are studying the frequency response of a system. So it refers to a steady state response of a system to a sinusoidal input. Uh, it includes all frequency. So what we do, we drive a transfer function, a sinusoidal transfer function, not the other one, and we study the transfer function for frequencies 0 to infinity. 0 to infinite hertz. Sorry. So we study the response of a system from 0 to hertz to infinity hertz. So let's say we have this displacement of a system, the output displacement, and this is frequency. So let's say this is 0 hertz, this is 10, this is 10,000, this is 100,000, and so on and so forth. So uh, we will get a kind of a plot, like maybe it is vibrating like this one, and then so we'll get to know in a certain frequency range our system will vibrate more compared to the other frequencies. So we will have a holistic view that okay, this frequency range is dangerous for my system. If the excitation force is in this frequency, my system will likely to undergo high amplitude of vibration, which may damage our system. So it gives us like a holistic picture of how our system behave and what are the safe and unsafe frequency ranges for my system. So let's start with one of example for our case. Uh, so let's take an example of if you just recall, let's assume we have a system with a spring at one end and there's a mass, and let's say it is being excited with a force which equals to P naught sine omega t. And if you try to drive its equation of motion, there is no damping, so it will become, I'm going to do it directly, mx double dot plus kx equals to p sine omega t. Just linearize this equation, divide by m so that we don't have any constant value with the maximum derivative, so it becomes x double dot plus k over m x equals to p over m sine of omega t. So if we solve this equation, you can take the Laplace transformation, this one, and if you solve this equation, you will, if you remember, you will have two types of solution. The first is called homogeneous solution, or in some cases it is also called as complementary solution, and second one is particular solution. So this tells the behavior of a system when it is vibrating at its own natural frequency, while this part of the solution tells us about the response of a system when it is being vibrated uh, due to the excitation force, external forcing. So we can solve the system and we will have two, let's say, two terms in our solution. The first will be because of the homogeneous solution, and second will be because of the particular solution. So in this case, we are not interested uh, in the complementary solution. Rather, we are more interested in the steady state solution, which is the particular solution. That this part tells us about the steady state response. So now we don't need to do an extra effort to solve the system for the whole solution, solving the homogeneous part and the particular part. We can directly use a sinusoidal transfer function to get the particular solution of our system without investing our time for the homogeneous part. So before going into that, let's try a problem so that we can have a quick look over that one. Let's assume we have a mass spring damper system, and that is equals to, yeah, let's assume we have a mass spring damper system here. Sorry. So we have a spring K and we have a damper B, and they both are connected to a mass M. That's K, that's B, and we are exciting it with a force of P equals to, let's call it Pt equals to P sine of omega t. Now, if you drive its equation of motion, it will become mx double dot plus bx dot plus kx equals to excitation force. uh, again we have to take the Laplace transform for this one. That will become ms square plus bs plus k into x of s equals to p s. I'm just assuming the zero initial condition. Then we know the the transfer function is the Laplace transform output over input. So output is x of s, input is ps. So it will become 1 over ms square. Sorry, become 1 over ms square plus bs plus k, and we can call it to be transfer function g of s. That's a transfer function for us, but we are interested in only the steady state part. So s equals to iota omega, and so we can write it as g iota omega. It will be equals to x iota omega and p iota omega. It will become equal to uh, m, and then iota omega square. Iota square would be minus 1, and it will be minus 1 into omega square plus b iota into omega plus k. We can just rewrite this one. It will become minus m omega square plus iota b omega plus k, and we can rewrite or rearrange this one as 1 over k minus m omega square. Just rearrange the real and the complex part. Well, that's a complex number, takes the form of complex number b omega. So if you remember, any complex number is equals to real part plus iota, or the imaginary part, you can say rc. So we have a real part and the imaginary part, so it takes again the form of that one. So once we have it, so we can have the steady state output solution for our system. That will be equals to a magnitude of uh, this transfer function into the applied sinusoidal force, but that will be equals to the applied load plus with some phase difference. So you should differ between the force that is being applied, that's the input force, but once the system receives that force, the system has some kind of lag. It's not like when you apply the force, system instantly starts to vibrate at the same frequency. When you have the damper, the damper will cause some lag between the applied load and the input load. So whenever you are writing the applied load for as a part of solution of the response of a system, you must add a phase angle, which is actually quantifying the lag between the input and the response of a system, and I will explain graphically what it is. So this is the total solution for our system, so we can rewrite this one as uh, x e equals to 1 over, okay, we have this one, okay, better to just find out them separately. So this is the amplitude of our transfer function, and that's a input load with some phase angle. So we need to know what the phase angle is. So amplitude of a complex number is equals to, whenever we want to find an amplitude or magnitude of a complex number, it becomes r square plus iota omega square. So that's how you can find out the magnitude of the complex number. Not this iota, sorry, plus the c square. So in this way you can find the magnitude of this transfer function as equals to 1 over, and we have, let's call this as r, let's call this only as c, not the iota. So it become under root of r square, that is k minus m omega square of square plus b omega square. So that's the magnitude of our transfer function. And in the same way we can calculate the, what you call, the phase angle of our uh, transfer function. So the phase angle of the transfer function can be written as 1 over k minus m omega square plus iota b omega, and which can be written as minus of tangent inverse, that is c over r, that is c over r. So that becomes b omega divided by k minus m omega. So whenever you want to find the phase angle for this one, it becomes tangent inverse c over r. So this is how we can now we can substitute both of these values, magnitude and the phase angle, in our solution, equation. So it becomes x of t would be equals to 1 over under root k minus m omega square plus b omega square, and we have into the p sine omega t plus phi. It becomes minus of tangent inverse b omega divided by k minus m omega square. Remember, this omega is a frequency of input force, not the natural frequency of a system. This is natural frequency of a system, which is equals to under root k over n. So we can simplify this one. That becomes equals to p divided by under root k minus m omega square plus b omega square into sine omega t minus tangent inverse b omega k minus m omega square. So this is the total solution of our system. Now we are done with the solution. But what was the purpose for us doing all of this exercise? We were interested in the frequency response of a system, and what we were exploring. We know that our system has reached a steady state, and now we are more interested in the at what frequency, what will be the amplitude of my vibration, or the vibration of the system, and what will be the lag between them. So I'm more interested in the amplitude of the vibrations and the phase shift between the with the different frequencies. So we can simplify the system and remove these absolute values and try to define them in the terms of ratios and dimensionless values, as we have done earlier to simplify our system. So we know k over m is equals to omega n square, and the damping divided by spring constant is equals to 2 into the damping ratio into the omega divided by omega n. So now we can simplify this one and substitute the values here. You can drive these values by yourself. So it will become x of t, and if you take k common from here, so it will become k square outside, and it will come outside the root, and it will be 1 minus m omega square divided by k plus it will be square omega square divided by k, and then we have sine of omega t minus tangent inverse, and we can again simply take the k as common. So here that will become b over k into omega, and 1 minus, because it will become omega square into m divided by k. And we can further simplify this one. Let's go to the next page. I'm going to copy We can further simplify this one. It will become x of t equals to p over k under root of 1 minus omega square by omega n square plus 2 into damping ratio into omega over omega n square sine of omega t minus tangent inverse. It will become 2 into damping ratio omega over omega n divided by 1 minus omega square over omega n square. You don't have to worry about this lengthy derivation. It's just to show you how we reach a particular solution. Here the p over k, it's called the static deflection, and I will let you know what it is. So we can write we are more interested in the amplitude ratio and the phase angle. So this is the amplitude at any vibration, at any frequency of input force, and this actually deflection of a system when the input force has zero frequency. It actually was not a dynamic loading, it was actually a simple push, you can call it. So whenever, let's say, of this input force of a same magnitude but with zero frequency was acting on the system, it will cause a static deflection, not a vibration, because it's simply not our sinusoidal force, it is just pushing the system. So at that particular point, this becomes the total amplitude becomes equal to p over k, and that becomes static deflection, because this becomes 0, so this whole become 1, this becomes 0, so this whole terms become 0, and so on and so forth. You can keep on plotting 0 here, so you will only left with p over k when the input frequency, when omega is equal to 0. I'm not talking about the omega n. So the amplitude ratio would be equals to the x divided by, it's called static deflection, xst, static deflection. So which is equals to 1 over only this part, 1 minus omega square over omega n square plus 2 into the amplitude damping ratio into omega over omega n square. And the same way you can find the phase angle. For this one, it becomes tangent inverse to damping ratio into omega divided by omega n divided by 1 minus omega over omega n square for both of them. So this is how you can find the response. So whenever we are evaluating the steady state response of a system, we are interested in identifying the amplitude ratio with the changing frequency of the input force. We are not interested in absolute value of amplitude, rather we are interested in amplitude ratio and the phase angle. How much lagging is there between the applied force and the system response. So if you remember, just to give a brief review of what do we mean by the phase angle. So we may have, let's say, 2 pi radians, right? Or the pi radian in the radians, you can say. So we know whenever, let's say, that's applied force and sorry, this system response. So let's say there was a load being applied onto a system, it was a sinusoidal force. So you have certain amplitude here and certain frequency up to infinity. Once that load interacts with the system and the system starts to respond, there will be some lagging. It won't start to respond instantly. So let's say we know the phasor is used to quantify this dynamic system. It tells us about the amplitude of a system. Initially phasor was here, then at particular point the phasor reach here, then after some point the phasor reach here, and so on and so forth. But there will be some kind of lag between the application of load and the system. So it will be maybe its crust doesn't matches the trough of, or the crust of applied load, and trough doesn't matches the trough of the applied load. So there will be some kind of lag between both of them. So now it was initially at the same place, but once it reaches here, our phasor is here at the maximum angle. Then at particular point our phasor is here, and then at this point our phasor is here. But if you draw the same phasor for the system response, it will be like initially it was here, and by the time it reaches here, and if you draw the same phasor for the applied load, so you will find some difference between them. So at that time, let's say at time t equals to 10, this was a phasor of the system response. But at time 10, the phasor of the applied load was this one. So there's a difference of what you call, uh, some lagging between the applied load and the system response. So we can quantify this angle. What is the angle between this and this? Maybe it's like uh, 3 by 4 of pi, because we know pi radians is equals to 180 degrees. So this makes up like 3 by 4th of the pi, and so on and so forth. So this is how you quantify the lagging between the applied load and the system response, using the radian scale, because the degree scale won't go beyond 360, so we use the radians for this one. So that was just a brief introduction of how we use the sinusoidal transfer function to study the steady state response of a system. And next we'll attempt some examples to check out how we can use it in for the different systems, and then we will move towards the frequency response of our systems, and when our system is vibrating with a steady state load, mostly in our rotating system, so how that load is transferred uh, to the surroundings, or to the other components that are somehow in contact with the vibrating system. Maybe let's say you are using a machine on the floor of a factory, so and that machine is vibrating with a very high amplitude and frequency, so that some part of that load will and the motion will be transferred to the base of the machine and even to the floor. So you can calculate the transmissibility of the force and the motion, and how you can avoid or reduce that transmissibility, that is using the vibration absorber. So you can have the dynamic absorbers, you can have the static absorbers, it depends upon your application. So we'll look into that one next. Now the next thing we are going to deal with is the vibration in the rotating systems, which is most of the cases in the mechanical systems, and the resulting transmittance of that vibration, maybe the motion of that vibration or the force because of that vibration to the surrounding systems, or vice versa. Maybe the motion and the force from the surroundings is transmitted to the a delicate system which we don't want to receive any external excitation. So that is a case of vibration isolation. So before jumping into that, we will discuss the case of vibration in the rotating system and the vibration control. So start with vibrations in rotating systems. Whenever we are dealing with the vibrating systems, before directly jumping to the rotating systems, so there's always obviously a source which is generating the vibration, then there's a path which is responsible for transmitting that vibration or the motion to a receiver. right? So there may be the case where the machine itself is a vibration source, and that machine is transmitting that vibration and the motion to the floor of the factory, as I mentioned before, and it is done through the contact, maybe the pad, something that is isolating the machine and the floor, or vice versa. Maybe you are dealing with the very delicate microscope. Let's say you have a table and that has a very delicate microscope over it, and that microscope needs to be taken care of. You don't want that if you're using and you mistakenly hit the table, so that table will move, this motion will be transmitted to this one, and it will move and it will disturb your reading. So obviously you don't want the vibration or the motion to be transmitted from the table to the microscope. So you will add a vibration control mechanism between the table and the microscope, so that it will not let the motion or the force transmitted to the microscope, so that it will not affect your reading. That's one of the examples. So the purpose of this was to mention that source can vary. Maybe sometime your machine is a source and the floor is the receiver, or in some cases maybe the base is the source and your instrument is a receiver. So you have to check what is more important for you. So in all of these cases, in both of these cases, you have different ways to isolate the vibration from the surrounding systems, and we will look into that one. Before jumping into that, we will see how a rotating unbalanced mass can generate a vibration in a system. So let's assume we have a rotating system like this one. Again, take example of let's assume it's again a washing machine. Let's say it's a washing machine, right? And that washing machine has a place where you can put in the clothes, and that will rotate at a certain RPMs based on the machine design. If you put the clothes here, and when the machine is rotating, your clothes are exactly at the center, then it's fine. It won't induce any vibration in your machine. But obviously, that's not the case. When they rotate, because of centrifugal force, the clothes get accumulated towards the sides of the machine, and then they rotate along the path. Just reduce. So, in that case, the center of mass of this lump of cloth, let's say the center of mass of this lump of cloth, does not coincide with the center of rotation. So there's a difference. There's a distance between them. So because of this distance, this rotating mass induces the vibration because of rotating motion. If it was coinciding with the center of rotation, then it won't induce any vibration. But since it doesn't, in reality, it doesn't coincide with it, it induces a vibration because of rotating motion. So we know the force that is causing that vibration is because of the centripetal force, which is equals to uh, omega square r, that's centripetal acceleration into the mass. And obviously it is because of the distance between the centrifugal force and the it is because of the distance between the center of mass of the lump of clothes and the center of rotation. So if let's say that machine is mounted on floor with and has a base which has a stiffness of K and the damping coefficient B, and that excitation amplitude is X, the total mass of the system is M. So we can write our equation of motion as capital M, mx double dot plus bx dot plus kx. And since the excitation force, let's call its magnitude equals to P, and that is dynamic loading. Let's say it has a P naught sine omega t amplitude. So we can call it P naught sine omega t. where this P naught is actually equals to this. So you can rewrite as mx double dot plus bx dot plus kx equals to m omega square r, where r is a distance between the center of mass and the center of rotation, sine omega t. Uh, that's it. So this is the general equation of our equation of motion, subject of a system that is subjected to the excitation because of the rotating mass, unbalanced mass, you can say. So you can take the transfer function for this one, and you will get, let's for now just call it as PS. So I can mx double dot plus bx dot plus kx, let's call it p of t. Now take the transfer function, do the Laplace transform and take the transfer function. You will get an expression of x of s divided by p of s equals to 1 over ms square plus bs plus k. And if, because we are interested, again we are interested not in the whole solution, rather we are interested only in the steady state part, so we will use s equals to iota omega, and because of that we will have iota omega divided by p iota omega equals to 1 divided by minus m omega square plus uh, that is iota b omega plus k. That's the transfer function or the sinusoidal transfer function. And you know how we can calculate the total response of a system, that is equals to the magnitude of transfer function into the phase angle. So we can write it as 1 divided by k minus m omega square plus b omega square, that's whole under root. And then we can rewrite this one as if I just choose the other way, just let's continue on this side or just move. Let's rewrite this part. So we know the total solution of our system, as we have seen earlier, would be equals to x sine omega t plus 5, and where this one is equals to the magnitude of the transfer function into sine omega into the force m omega square r sine omega t minus of tangent inverse b omega divided by k minus capital M omega square. You know the m is that mass of total system, where small m is the unbalanced mass. So we can write as m omega square r divided by under root k minus m omega square plus b square omega square into sine of omega t minus tangent inverse b omega divided by k minus capital M omega square. Just to clarify that small m is unbalanced rotating mass, capital M is mass of whole system, and omega is excitation frequency, not the natural frequency. That's it. That's the total solution. You can further simplify as we have done earlier, just to remove these k and b's and define that system in terms of uh, ratios and dimensionless numbers. So you can find the final solution equals to m omega square r over k divided by under root 1 minus omega square by omega n square whole square plus 2 damping ratio omega divided by omega n into the sine omega t, that's natural frequency, minus tangent inverse 2 into the natural ratio of the damping coefficient divided by omega n divided by 1 minus omega square divided by omega n square natural frequency square. So that's the complete solution of a system that is being excited because of the unbalanced rotating mass. So that's one of the scenario. We may have the different scenario as I discussed earlier. Maybe our system is not the source of vibration, rather the base can be also source of vibration. So in this case, because of this unbalanced mass, there's a generation of force which is being transmitted to the flow, or in some cases a floor may have some vibration and it is transmitted to our system, as I have mentioned in the case of microscope. So we have different ways to isolate the system from the surrounding. So let's say we have a system which is placed on a floor and it has some input force f naught sine omega t. It may be of for different reason, maybe an unbalanced rotating mass, maybe some other reason. So we can isolate our source from the surrounding by adding isolator spring, or we can add an inertial block as well, just to shift the natural frequency, or we can add a seismic block, like in case if a base is moving and we want to isolate our system, we want to protect our system, like in the case of buildings or like in the case of the, as I mentioned, microscopes. So we add a seismic block between the moving base or vibrating base and the instrument or the our system. This is how we isolate our system and from surrounding to reduce the motion and the force transmission between the system and the surrounding. So and that is called vibration isolation. That's called a vibration isolation. So obviously you need to first analyze your system using the sinusoidal transfer functions. You need to know about the natural frequency of a system. You need to know about the how you can find out, like, if the certain stiffness of spring you're adding, are they going to go do any benefit to our vibration isolation efforts, or they're not. So you have to solve the systems and find out the system motion based on applied frequencies and the natural frequencies and the system dynamics, and then you can try different scenarios and find out the response of a system. So no, once a system is vibrating, there can be two cases. The first is there is a force excitation, there's a transmission of force to the surrounding, or there's a transmission of motion to the surrounding as well. So there are two different ways to calculate this one. So the next we are going to look into how we can calculate the transmitted force and the transmitted motion between the surrounding and the system. Now the next topic is the transmissibility. So we have so far studied how we can determine the steady state response of a system when it is subjected to the sinusoidal excitation or any harmonic excitation, and based on that we found out certain criterias uh, by using which we evaluate the response of a steady state response of a system, that is amplitude ratio and the phase angle. And then we move towards a kind of practical application of that one, and we assume that, let's suppose there's a rotating unbalanced mass in a system, and because of that unbalanced mass and it is rotating, so it naturally exerting kind of centrifugal force, and that centrifugal or centripetal force is causing vibration in the system. And so how we can evaluate that vibration of a system being produced by that unbalanced mass. Now the next topic is, once that vibration has been produced by that unbalanced mass, so naturally it will be transmitted to surroundings. So that's we call transmissibility. So that's what we call transmissibility in our case. uh, let's start with that one. So it's a kind of a measure. It's a measure of how much motion or how much force has been transmitted from the source to the receiver. So mostly the vibration is your system, and the foundation is a receiver. Or if there's a motion transmittance, then it's likely the motion of the foundation which is being transmitted to your system, like the case of microscope. So we can calculate both of them. So if the source of a vibration is a vibrating force due to an unbalanced mass, so then the transmissibility will be the ratio of transmitted force. Let's say you have a same machine with kind of unbalanced mass that is rotating in in a circular pathway, and you have a mass spring damper system that is isolating the system from the foundation. And because of this centrifugal force and unbalanced rotating mass, there's some force that has been generated, so it will be transmitted to the foundation. So the transmissibility of for force excitation can be written as, you can call it Tr, that is equal to amplitude of the transmitted force divided by amplitude of the excitation force. So it's again output over input. It's a ratio between output over input. Here output is the force that is being transmitted to the foundation, and input is the force that is being generated by the system due to some reasons. So it is amplitude of the transmitted force divided by the amplitude of excitation force. So we can, like in the case of motion generated by the unbalanced mass, by the force of the unbalanced mass, we determine two criteria. That's the amplitude ratio and the phase angle by which we classify the steady state response of a system because of this. So there are two different measures to that help us to classify the transmittance of force and the motion into the system. So the one again is the same damping ratio we are well aware of, and the other is frequency ratio. In the previously we discussed about the amplitude ratio. Now we have the frequency ratio that is represented by beta. So it's omega divided by omega n. So let's assume we have an unbalanced mass, and that is generating some force, and which is being transmitted to the foundation through a spring with a spring constant K, and the damper with a damping constant B, and there's some excitation X in this direction. So we know that the excitation force, let's say it is P, which is equals to m omega square r sine omega t. That actual one we can write it as f naught sine omega t, where f naught is equal to m omega square r. So writing the equation of motion for this system, as we know, it will be, and let's say this capital M is the mass of whole system, so mx double dot plus bx dot plus kx equals to the force, and where m is the total mass of a system. Now that is the input force. Now the force that is being transmitted to the ground, let's say there's a resultant force that is acting in this direction. There's a resultant force acting in this direction. So it will be opposed by the spring force and the damper force. right? So we can write that as, uh, let's say we say downward is positive, so it will be f of t minus f of s minus f of d equals to 0, or fs plus fd equals to ft in time domain force, and then we have kx plus bx dot equals to ft again, which also be in the sinusoidal nature, because the input force is also sinusoidal in nature. So it will be ft sine omega t. Now we will have some phase angle as well. There's some lagging between them because there's a damper here. So now we have two equations. We have one equation, let's call it 1. We have another equation, let's call it equation 2. So we can now take the Laplace transformation. Again, recall our main purpose is to get the ratio between the transmitted force Ft and the excitation force F naught. You can call it this F naught or PS, whatever you like. So for that we move towards the transfer function. So let's say for equation 1, it will become ms square plus bs plus k whole into x of s. That is the output, and that's input force. So that's output over input. It will be equal to 1 over ms square plus bs plus k. Now for the second system, we know that in this case, because of this force that is being generated here, because of unbalanced mass, the system will move in downward direction, or it will excite in particular direction, and that excitation is causing the transmitted force. So now we have we can write equation number 2 as what is it? Yeah, b x of s. Sorry, we can write equation 2 as bs plus k into x of s equals to f of s, whatever I just call it, this whole force, let's call it transmitted force. So it become f of s, so we can write it as x of s over f of s equals to 1 over bs plus k. 1 over bs plus k. Now if we can find the ratio between the transmitted force, that is the output, divided by p of s input. So all we can do is eliminating the x of s from the system. So let's invert any of this. Let's write it as f of s over x of s equals to bs plus k. And now we can multiply equation 2 and equation 1. So let's jump to the new page. Now multiplying equation 1 and equation 2 post Laplace transform. So it will become fs ps equals to fs over x of s into x of s over p of s, and obviously it will cancel out, so we will have at the end as bs plus k divided by ms square plus bs plus k. So that's Laplace transform ratio between the transmitted force and the applied force. And since we are interested in the sinusoidal transfer function, only the steady-state response of a system, so we can say s equals to iota omega. So it will be f equals to iota omega divided by p iota omega. That becomes b iota omega plus k, and become minus m omega square plus iota b omega plus k. We can do the same simplification as we did earlier. Just try to linearize this one. It will become b over m, and that's iota omega plus km divided by minus omega square plus b over m uh, iota omega plus k over m. And we can substitute, again we are interested in the dimensionless number as much as possible, so k over m is actually the natural frequency square of the system, and again the b over m is 2 into the uh, damping ratio into the natural frequency of a system. So it can be written as f iota omega divided by p iota omega equals to 1 plus, I'm not going to do all the steps again, we did last time, 2 into the damping coefficient omega over omega n, again the natural frequency of a system again, and the frequency of the excitation force, 1 minus omega over omega n square plus iota 2 into damping ratio omega over omega n. So that's what we have, and here we introduce frequency coefficient, frequency ratio, that is frequency of the excitation force divided by frequency, natural frequency of a system. So we can rewrite this as, uh, before going into that, I think just take the amplitude of this one. So because amplitude is a constant value, so you have to take the amplitude of this one, so it will become f iota omega divided by p iota omega. It will become equals to 1 plus 2, sorry, 1 plus 2 damping ratio omega over omega n square divided by it's 1 minus omega square over omega n square whole square plus 2 damping ratio omega over omega n square. So you can replace omega over omega n by beta. So it can be rewritten as under root 1 plus 2 damping ratio into beta divided by under root of 1 minus beta square whole square plus 2 into damping ratio into beta square. So this is the transmitted force divided by the damping force. That's the final form for this one. I think we missed something. That's square term, not the linear term. So you in a lot of your mechanical vibration books, you will find the curves between the damping ratio and the transmissibility. So that's equal to transmissibility, and it's equal to amplitude of uh, transmitted force divided by amplitude of excitation force. So you know it totally depends on the damping ratio and not the damping ratio and the frequency ratio. So in a lot of cases, you will find graphs in your vibration books like this one. So this is how, if you keep on changing the value of frequency ratio, this is how your transmissibility will change. The higher the frequency ratio is, keeping the damping ratio constant, your transmissibility will increase. Let's say if you maintain the damping ratio at 1, so as soon as you keep on increasing the what you call the damping ratio, the frequency ratio, the transmissibility of the system is increasing, more force is being transmitted. Once the excitation frequency and the natural frequency of the system becomes equal, then after that you will see a decline in the transmissibility of the force, because you're moving away, again you're moving away from the resonance. And in the same case, if you keep the damping frequency ratio as constant value, then your transmissibility will increase with the reduction in damping. So here it was 1, it at 0.5 you will see higher transmissibility, and at 0.2 you will see even higher transmissibility, and at 0 you will find even like almost infinite transmissibility. So so if you keep the damping frequency ratio constant and you reduce the damping to the system, naturally more force will be transmitted. But if you for the constant frequency ratio, if you add on damping in the system, obviously the transmitted force will be damped out by the dampers. This is what dampers are for, to damp out the energy so that you don't transmit that energy to the flow. So maybe you will encounter some problems in mechanical vibration where you have to consult this graph and to pick up the values, and maybe in your exam, in your assignment, or maybe you have to draw this graph like for few uh, terms. So now you know how you can read this graph. I hope you won't fear from this graph. Let's try an example. Now assume we have a system with certain mass and stiffness. Let me copy it here. Yeah. So assume we have a rigid body that is mounted on an isolator to reduce vibratory effects. Assume that the mass of the rigid body is 500 kilograms. So we have capital M is equal to 500 kg, and the damping coefficient of the isolator is very small. So we have the damping coefficient equals to 0.01, and the effective spring constant is 12.5. Sorry, 12,500 Newton per meter. Find the percentage of motion transmitted to the body if the frequency of the motion acceleration of the base of the isolator is radians per second, 20 radians per second. So we have frequency of excitation is 20 radians per second. Uh, we have the mass, we have the spring constant, we can find the natural frequency, that is equals to under root k over k m, and that is 12,500 divided by 500 kilograms, and you can solve it. It will be equals to 5 radians per second. So we have the frequency ratio equals to omega over omega n, that is 20 divided by 5, that is equals to 4. And so we can directly use that transmissibility, that is equals to under root of here it is 1 plus 2 damping coefficient into the frequency ratio square, and so on and so forth. So we can rewrite that one. It's 1 plus 2 into the damping ratio into the frequency ratio square divided by under root 1 minus frequency ratio square whole square plus 2 into the damping ratios into the frequency ratio square. So you can substitute this value. You know the value of damping ratio, you have the value of frequency ratio. So we can substitute that one. That becomes equals to 1 plus 2 into 0.01 into 4 squared divided by 1 minus 4 square plus 2 into 0.01 into 4 square, and that makes up equals to 0.0669, and if you multiply by 100 it becomes 2, it becomes the oscillator reduces the vibratory motion of the rigid body by to 6.69%. So that's the total percentage of transmissibility of this force. So whatever the force is being generated, only 6.69% of the force is being transmitted to the base. So this is how you can calculate the transmissibility of the force. Now there are other cases where the motion is also being transmitted. That's called the transmissibility of the motion excitation. So let's look into that as well. Let's rewrite. That's transmissibility of the for motion excitation. So in the mechanical system, as we have seen earlier, the motion of the body is the vertical direction only. Uh, the system we have seen earlier, I don't know where is it. Yeah. Let's assume, I'll just redraw the system here. Let's assume we have a system of mass m, and we have some spring and some damping coefficient, and it is connected to a foundation, and that foundation has some motion. Right? So let's assume we have this motion in the foundation and it's in the vertical direction. So the motion PT at point A, let's call it at point A, is actually the input to the system, and the vertical motion xt of the body, let's say this one is the vertical motion of the body, is the output. So there's excitation coming from the base, and because of that there's some motion in the output. A common example is the example of microscope. So if you have placed a microscope on a table, if you just give some disturbance to your table, it will be transmitted to your microscope and you won't be able to observe your tiny particles. So this displacement is measured from the equilibrium position in the absence of this excitation force. So, and we assume that this excitation is the sinusoidal in nature, where Pt is equals to P sine omega t. So here we can rewrite make the equation of motion for our system, and we can write it as mx double dot plus b x dot minus v dot, because we have two independent coordinates here, plus k x minus p equals to 0, or you can rewrite as mx double dot plus bx dot plus kx. That's the equation of motion of our system itself, equals to bp dot plus kp. That's the dynamics of the excitation of the base. So you can take the Laplace transformation of this one. We are more interested in the output over the input. So we can take the Laplace transformation for this one, become ms square plus bs plus k, that's equal to x of s, and becomes bs plus k and p of s. I want to have x of s over p of s, so we can rewrite this one as bs plus k divided by ms square plus bs plus k. So that's motion transmissibility, and again we are interested in the steady state response of our system, so we can rewrite this one as x iota omega divided by p iota omega. Although if you want to solve at this stage, it's perfectly fine, it will give you the total solution, the transient and the steady state, but currently we are interested in the steady state response only. So it will become iota b omega plus k divided by minus m omega square plus iota b omega plus k. So again we can further simplify this equation. That's the amplitude of the output displacement divided by amplitude of the input displacement. So it can be rewritten as, I'm just omitting the simplification steps as we have seen it twice earlier. So it will become b square omega square plus k square divided by under root k minus m omega square plus 2 into the damping ratio into the uh, frequency ratio. Sorry, not this one. It will become b square over omega or into the omega square, and then you can further simplify this one to get the final solution. Amplitude of the output displacement divided by amplitude of the input displacement, that becomes equals to under root 1 plus 2 into the frequency damping ratio divided by into the frequency ratio square divided by under root 1 minus frequency ratio square and to the whole square plus 2 into the damping ratio into the frequency ratio whole square. So that's the how we can calculate the motion transmissibility because of the motion of the any base. So this was the topic of this lecture, where today we studied about the frequency domain analysis. So we studied like there was a general transfer function which gave us the holistic view of the response of a system, including the transient and the steady state. But just to reduce our work, we don't have to do a lot of work, so we are more concerned with the steady state response, which is like a long term behavior of a system if it is subjected to any excitation force, primarily sinusoidal force. So S equals to gamma plus iota omega, so we are not interested in the gamma, that is, or the sigma, that is actually the transient part of the solution. So we are interested in only iota omega, which tells us about the steady state part of the solution. So rest is the simple mathematical simplification because iota square is equals to minus 1. So and we simply after uh, rearranging all the terms, we transform the whole expression into the dimensionless quantities as much as possible. So we use the amplitude ratio, we use the frequency ratio, we use the damping ratio, so because they help us to easily classify the system instead of calculating each and every variable separately. And after that, once we are aware that how we can calculate the steady state response of a system without indulging into the calculation of the transient one, we studied how unbalance within the system can generate a certain force which can cause a vibration, and that vibration can be transmitted to the surrounding as well. So we initially see how a rotating unbalanced mass can be a cause of a sinusoidal excitation input to the system, and we quantified that the response of a system based on the excitation force that was generated because of the unbalanced mass. And then we knew that that unbalance that force that is being generated because of that unbalanced mass will be transmitted to surrounding. How we can isolate those surrounding with the machine or the instrument we are using, and how we can quantify how much force is being transmitted, how much motion is being transmitted from the machine to the surrounding or from the surrounding to the machine. So we saw transmissibility of force and transmissibility of the motion. So that's all for this lecture. Should you have any question, just write me on WhatsApp. I again apologize. I was not able to upload lecture last week because of some personal reasons, and I'll be uploading assignment as well. So now we are left with only one major topic in the discrete for the rigid body vibrations, that is the modal analysis. After that, we'll start with the continuous vibrations, like vibration of beams, where the mass is not considered or not assumed to be concentrated in this block, because obviously when you have a beam, you cannot represent beam by a small mass because we are assuming that there is no dimension of this mass. We're just representing this mass as a point source. Point source. So, and we are doing all the calculation based on that. But in reality, you have the bodies which are three-dimensional, so mass is distributed all along the body. So you cannot use this point source analogy to solve the dynamic behavior of those systems. So we'll look into the continuous vibration systems. That's all for this lecture. Should you have any questions, just let me know. Salam alaikum.